All right, everybody, we're going to get started with the first session here. This session is on design tools. We have 6 talks, and our first talk is going to be presented by Kevin Laeufer. Did I get your name right? Yeah. Close enough? Okay. Kevin Laeufer. Kevin Laeufer is a PhD candidate at Berkeley. And he thinks that software has it good with all of the great tools that they have, and there should be better options for RTL developers. He contributes to Chisel and is the maintainer of Chisel Test, and he apparently is heavily invested in the Chisel project. And he's going to be talking today about simulator independent coverage for RTL hardware languages. So, okay, Kevin, take it away.
Okay, thank you for the introduction, and thank you everyone for coming. I'm Kevin. I'm going to talk to you about our paper on simulator independent coverage. So first of all, let's talk about what is coverage? Why do I need coverage? What is it for? So let's assume you just created your own cool hardware design in, for example, a hardware description language like Chisel, but also maybe some other hardware language. You wrote a test, it passes, and now the question is like, does that mean I'm done? Does that mean my design works? Or is my test maybe missing some situations? And so one very classic answer to this question is, well, we wrote all these statements in our code. Let's see that at least every statement is useful. Every statement is used in the test, and that translates to line coverage. Now, the question is like, how do we do line coverage nowadays in Chisel? The way we do it is we use our Fertile compiler, compile things down to Verilog, and then we run things for an open source Verilog simulator like Verilator, and that will give us toggle and line coverage. However, there's a little problem here. The line coverage that we get is not the line coverage on the code that we wrote, it's the line coverage on the code that the compiler generated. This can be a problem, for example, in this situation where we have a very simple mux that's described with this like when statement, which is essentially like an if in Verilog. And here we see that this gets compiled down to this ternary operator in Verilog, which is totally fine. It maintains the semantics of the circuit. It's a correct compilation. However, it does change the meaning of line coverage because now you have one line that's always covered versus these 2 different lines that get covered depending on the value of the in signal. So what we note is line coverage is a property of the code that the developer writes. So it's kind of not a good idea to do line coverage on the generated code from the compiler. There's another much bigger problem, actually, which is that we also have some more native simulators in the Fertile ecosystem. So Fertile is our IR that we use with Chisel. For example, there's a treadle interpreter, which is super important if you have a lot of small unit tests, because Verilator takes a long time to start up. Treadle starts up quickly, so if you have a lot of small unit tests, use Treadle. On the other end of the spectrum is FireSim, which is useful if you have a huge SOC and you want to run billions of cycles. It takes forever to compile. It takes like 12 hours to map your design to the FPGA, but then it runs really quickly. You can boot Linux, and that's great. Unfortunately, neither of these simulators support any coverage at all right now because people writing them were just basically were just focused on correctness and on speed. Now the question is like, if we took like the page out of the playbook of like all the Verilog simulators, then we would have to write independent implementations of all these coverage metrics for each simulator. And that just sounds like a whole lot of work. And we're academics, we don't have a lot of time, we're lazy, we don't want to do that much work. So the observation that we made is we have this compiler already. We have this Fertile compiler that we use. And basically coverage metrics are kind of just like instrumentation passes in the compiler. So the question is like, can we just move everything into the compiler? Because then we only need to write it once. Now, if we want to do that, we have to think a little bit more about what's the interface between our compiler and our simulator. What is the thing that is supported by the simulator? So something that's supported across all simulators is synthesizable RTL, because that's the core thing that they're supposed to simulate. And we discovered that there's only one other thing that we need to add, namely this cover statement. And we'll go into the details in a minute. And basically, then we need to say, OK, if you have these cover statements, make sure that you print out the cover counts at the end of simulation. And then we can move all our instrumentation into the compiler. We don't care about which simulator you run. We just care about the simulator satisfying our interface. And then we have a report generator that also doesn't care about what simulator the values came from. Now, how does the cover statement work? So this is a small example in our Fertile IR. The cover statement has a clock, it has a predicate, it has a unique name. And then if you want to lower it into structural RTL, you basically just combine the path condition with the predicate into a new predicate. And then the way it works in a simulator is every time a clock event happens on that clock, we check the predicate. If it's true, we increment the count. And in the end, we report the count as a map from unique name to count so that you can know exactly which cover statement was active how many times. Okay, cool. So now that I defined this interface, let's see how we can use this to implement line coverage in our Fertile compiler. So going back to the same example we had before, we have these two lines and they get covered under different conditions. So how do we do it? Well, so this is what it looks like when we compile things down to a high level Fertile IR. And you see there's like there are the different blocks, and here there is some annotation on like what lines of Scala these statements correspond to. So what we do is we add a cover statement under each branch. We name them some automatically generated names, and then we look at all the statements under that branch and look at what lines are covered by them. And we note down that information. So we have this metadata that says cover statement L0 corresponds to line 11. If there were more statements in there, it would just be multiple lines here. Then we can run this whole thing through a simulator with any test bench that you want. And the simulator at the end will report these counts in our standardized format. And then we put those things together with the report generator, which says, for example, here, L0 was covered 10 times. So that means line 11 was covered 10 times. And then we can turn this into a human readable coverage report. And you see, it doesn't really matter what simulator we're using here. It could be a fast one, could be a slow one, as long as they like satisfy our interface. So we can implement a whole bunch of different coverage metrics this way. And our paper has all the details, and also the poster later, the poster session has all the details. So if you want to get into that with me, I'm happy to talk to you about this. For this presentation, I want to focus on how do we actually implement this cover statement across different simulators and what's the overhead. So first of all, let's look at Verilog. For Verilog, the implementation is fairly simple because there exists a cover statement in Verilog. This was never meant as like a compiler IR construct. It's more of a way for the user to say, oh, there's this certain signal I care about, and I want to know how often it's covered. However, we can use it for our purpose, and then Verilog will just like happily accept our automatically compiler generated cover statements. It will give us a coverage report. We kind of parse that and translate it back into our standardized format. And so now suddenly Verilog becomes like a simulator that adheres to the interface that we defined. Now, of course, we like add this layer of abstraction, which is nice for saving us some work. But the question is like, does this lead to slower simulations? That's like the iron law of computer science, right? You add a layer of abstraction, it gets slower, but more useful maybe. So we tried to benchmark this. We took some medium size chisel designs that are open source. We tried to find somewhat longer running tests, and we tried to remove the test bench overhead, because sometimes the code that drives your simulation actually can make things like 100 times slower. So we removed that. And so basically what we report is almost raw simulation overhead. So the overhead here is in percentage of runtime. So comparing no instrumentation versus some different instrumentations. The important things to focus on here is in red, we have line coverage on the generated Verilog in Verilog, versus green here is our line coverage from the Fertile compiler. That's the chisel line coverage. And we just measure the overhead. We see that it's kind of coming out to the same thing. I don't want to declare a winner here, and it also depends a little bit on what compiler versions you use. But basically, the gist of it is that the overhead is negligible, and we see the same thing is also true for toggle coverage here. Now, one simulator that's much more interesting to support is FireSim. So FireSim, as we said, maps your whole design to a cycle-accurate FPGA simulation, or to a cycle-accurate simulation on an FPGA. And so we need to actually turn our cover statement into something that can be mapped to an FPGA. So we have a clock, we have the predicate, and what we do is we make a counter. And it's not shown here, but it has to be a saturating counter so that you don't just go back to 0 at some point. And then the way we get all these values off the FPGA is we connect all the counters into a scan chain. We have a software component that controls that. So at the end of simulation, we just scan out all the values. And then the software component will actually like make sure that you get the exact same output that you get from Verilog. So your FPGA accelerated simulator gives you the exact same interface than your Verilog simulator or like other simulators that we have. So what's the overhead here? So FireSim never had any coverage metrics, so we cannot compare to like native coverage or something like that. But the question is basically like, can I enable this all the time? Is this something that I want to do? So here we actually like vary the bit width of the counters. So the counters are saturating. So if you have a 2-bit counter, it means it will get stuck at 3. It will not be able to report more than 3 times that something is covered. If you want to have full resolution, like for booting Linux and like running for billions of cycles, you actually do need a 48-bit counter, but that is a little unrealistic. As we can see, it actually like means that some designs won't fit on your FPGA anymore. It more than doubles your resource usage. However, if you only care about whether something is covered or not, then like having a small counter actually gives you like almost negligible overhead. And so I think this is like a realistic application here. One good news is that, so this is like for line coverage instrumentation. So you get about 8,000 cover points, and scanning them out just takes a couple of milliseconds. So you could actually do things where you like have different phases of your simulation, and you just like scan out and reset the counters at different points in your simulation. Okay, so now we have this cool system. And I want to just like visualize a little bit like what this abstraction provides us with. So this is where we started at. We had variolator and we had line and toggle coverage, and the line coverage is the line coverage on a generated Verilog, not on a chisel. Then we added like all the support for variolator, for the treadle interpreter, and we added line and toggle coverage passes, and that was like a major amount of our work. But then it kind of paid off, because if we add new coverage metrics, we only need to write an instrumentation pass, and it immediately works on all the simulators that we support. If we add a new simulator, it automatically works with all the coverage passes that we wrote. And so this way, we basically added a whole bunch of different coverage metrics, different simulator support. And so the final thing we did is, after we were really familiar with the system, we tried to look at Essen, which is a really cool research simulator that the next talk is actually going to be about. And there, we basically tried to see how quickly can we implement the support for this cover statement, rudimentary support for the cover statement. And it took us about a day of work. And I call it sort of like the power of abstraction, right? Like, because we decoupled coverage metric from simulator support, we can suddenly take advantage of all this work that we did before. Other things that I wanted to mention real quick is, we did this in a chisel ecosystem, but I think this is applicable to a lot of other new and old hardware languages. So if you have your new hardware language, you could add similar coverage passes on a cover statement. And I also even think that if we had a single system Verilog compiler frontend that everyone was using, we could also do the coverage instrumentation there. Also, you can use this for feedback-directed fuzz testing. There's a little paragraph in the paper. Basically, instead of feeding the counts into a report generator, you feed them into a fuzzing loop, and then you can do fuzzing on your design. You can trivially merge coverage across simulators, because now we use the same instrumentation. So all the counts are the same on every simulator. So you can merge things. And you can, you might have earlier seen there's like a Yosis formal backend. So you can use Yosis to generate inputs using an SMT solver to like maximize your line coverage, for example. Thank you very much for listening. And I'm happy to take any questions now.